This is example 10. And this is, I think this is one of the easier related rates problems, but I often hear back from students who've gone off to university and go, that shadow problem, I still can't wrap my head around it. It's a very specialized use of related rates. And I will tell you right now, and maybe this is what makes it weird, is when are you allowed to use this 9 meters? Forget about what the question is about. It's about a shadow shrinking, and we'll get to the details of that. But it says, how quickly is the tip of the shadow moving when the man is 9 meters from the lamp? When are we allowed to use that 9 meters? When are you allowed in this question to use a height of 3 meters? When are you allowed in this question to use the 2 meters for the bottom distance? After you differentiate. Okay, that's always the case. Those variable values, the values that a variable has at a particular point in time, are only useful after you differentiate. And I think the thing that makes this shadow problem weird is you are never going to use that 9 meters. Because it turns out that after you differentiate, that variable will go away because the relationship is linear to begin with. Okay. So let's talk about what's going on here. We have an 8-meter tall man that's walking towards an 8-meter tall street lamp. Did I just say an 8-meter tall man? We have a 2-meter tall man walking towards an 8-meter tall street lamp. So if we draw a representation of this, this is the street lamp. This is the sidewalk or the pavement or the road. And you have a man who is 2 meters tall. Still pretty tall, certainly not 8 meters tall. And I don't know, that looks like in relation it could be 8. If you want to nitpick and say maybe it should be a little smaller, if you want to get out a ruler, I suppose we could do that. Well, that, eh? 8. That's close enough. Thank you very much. So this is the person over here. This is the man. I don't think we need to label it. This is the street light. There's a light source at the top here, and of course the light source creates shadows whenever the light is blocked from hitting a surface. So when that light, and please don't draw all of this, it's going to get really messy. When that light travels in this direction, that's a horrible color, travels in this direction, it strikes the ground and there's no shadow there. When the light travels in this direction, same thing, same thing, same thing. Well, it's not hitting the ground, but it's hitting the man. It's lighting up the man, his front or his back. But what's going to happen is, and the light is going to reach there, there's going to be some point right here where it's going to create a shadow because the light is prevented from hitting the ground. Okay, and that's, I think, what we need to draw on this diagram. But you don't need a big, thick line like that. What we can do is we can say that this line represents kind of the critical line of light where you're going to have a shadow down here at the bottom. And we can start adding things here. We can add 8 meters for this height. We can add 2 meters for this height. I would tell you that in post-secondary there are shadow problems where instead of having a lamp post, what you have is a glowing object, a light bulb that's glowing, and you drop it, and it's moving down at the same time. It's accelerating. So things can get more complicated. And we're going to encounter, I think, that problem at some point, just as an additional kind of exercise if we want to take a look at it. We're allowed to put in 8 meters for the height of the lamppost or the height of the light above the ground because it doesn't change. We're allowed to put in 2 meters because the man is not growing significantly as he's walking. Now, what are we asked to determine? We're asked to determine the rate at which the tip of the shadow is moving at a particular point in time and how fast the shadow is shrinking. This is maybe one of the more complicated things that I have to try to explain. And some of you will pick up on it right away. That's the shadow. And this is the tip of the shadow. And the tip of the shadow is going to be moving. The man is walking. First of all, why is the shadow changing size? Because, let's face it, it says find the rate at which the length of the shadow is changing. In fact, we would probably want to call this S. I'm going to call it S. It's a variable. The shadow is going to be changing length. Why? Christy? Yeah, the length of the shadow depends on where the man is. Like right now, if the man is there, that's the shadow. And I don't want you to change anything in your diagram. I'm just pointing out that if we were to move the man over here, whether he's walking towards the lamppost and that's where he ends up, or maybe he starts here and is moving away, I haven't looked and it's not that important yet. But if that's the case, then the length of the shadow is pretty short. That's why the length of a person's shadow at night from the sun, as the sun is going down, is very long. Because the angle that the light is clipping the top of you is not quite horizontal, but it's more to horizontal, and it creates a longer shadow. You know, on the other hand, if the man is still 2 meters tall and is way over here, then we're going to have a very long shadow. So if I asked you, why is the tip of the shadow moving? I suppose you could say that the tip of the shadow is moving because the shadow is, let's get this straight. Is he walking towards or away? Towards. So the shadow is shrinking, right? So you could argue that the tip of the shadow is moving because the shadow is getting shorter, right? But if you look at my fingertips here, this is the length of the shadow right now. This is not how the length of the shadow is getting shorter. Right? The tip is moving because the shadow is getting shorter, but, and this is going to be like chewing bubble gum and tapping the top of my head at the same time, this tip is getting in a different location. It's moving because the shadow is shrinking and the man is moving. So there's a difference between saying how quickly is the shadow shrinking and how quickly is the end moving. But we're going to start off with finding ds dt, which is the rate at which the length of the shadow changes. So we're looking at ds dt. We need another rate of change. You cannot find a missing rate of change in calculus if you don't have another rate of change. Well, the rate of change is that the man is moving. So what is the speed of the man? The speed of the man is 1 meter per second. But we need to measure that speed as being a rate of change of a distance. What distance? Well, why don't we call this distance x? Because then if the man is starting in this particular position here, and it doesn't matter where he starts, this is a general diagram, and he's walking toward the lamppost at a rate of 1 meter per second, what that means is that dx dt equals -1. That distance x is shrinking at 1 meter per second. I have a question for you. Will the tip of the shadow be moving faster than 1 meter per second? Sure. Because the shadow is getting smaller and he's dragging the whole shadow this way at 1 meter per second. Okay. It's like me reeling in a fish while the boat is moving in the opposite direction. The fish really moves faster. Anyway, now I'm going to leave this in your capable hands for a couple of minutes. We need a relation between S and X. Go. You guys are smart. I want to see if you can figure this out. We want a relationship, a mathematical relationship between S and X. And they say, and I tend to agree, that if students can figure something out on their own, they're more likely to be successful using it later. Not everybody will be able to figure this out, but I'm going to give you a couple minutes to see if you can come up with something. The hint I will give you is, even though the equation is not going to be that pleasant to work with initially, how you develop it is a grade 7, 8, 9 kind of idea. It has nothing to do with higher level math. It has nothing to do with trigonometry, not directly. Fazile, what are you thinking?
2 over s is equal to 8 over x plus s.
It's a ratio. You have two triangles here. It's perfect. You have two triangles. This triangle and this triangle. Just offsetting things a bit here so you can see them. And those two triangles are similar. What does that mean in this context? It means the larger triangle is a scaled up ratio of the smaller triangle, which means, and there's so many ratios you could talk about here, you could say the height of the big over the height of the small equals the base of the big over the base of the small. I think, Fazile, what you said was 2 over 8.
2 over x.
2 over, okay, so that's another way to do it. We don't have to write small over big equals small over big. You can write ratios of corresponding sides. That 2 divided by s, which by the way is the tangent of this angle, must be equal to 8 divided by s plus x, which by the way is the tangent of this angle, but it's the same angle. That's why I said it's not trigonometry, but you could justify it with trigonometry. It is a ratio that we're using to come up with the connection. We're saying the height of the small over the base of the small. Some people prefer not to use s, because if there's 5s involved, it might be confusing. Equals the height of the large triangle over the base of the large triangle. And there's your formula. And once you have this, this question is simple. It really is. You cross multiply. You know me, I'm not a fan of cross multiplication, but sometimes it's just simpler to say we're going to cross multiply. Particularly at this level. You know, you go through that math 20 phase where I say don't cross multiply. We know enough about math now to know why it works. That looks okay, 2s plus 2x. Oh, I can subtract 2s from both sides and get 2x equals 6s. I don't have to, but I could divide both sides by 2 to make things even simpler. And I get x equals 3s. Man, it's a linear relationship. It's not even quadratic. Never mind more complicated. Differentiate now. Dx dt equals 3 ds dt. So this is what I was referring to. There's no variables left after you differentiate. There are rates of change of variables, but there's no s or x. So it doesn't matter where the man is. 9 meters, 3 meters from the lamppost, who cares? What this is telling you, well, let's finish the problem. dx dt is -1. So that means -1 is equal to 3 ds dt. So ds dt in this situation is -1/3. Was he walking in meters per second? Of a meter per second. This is one of the only cases, the only one I know of off the top of my head, where you do a related rates problem in calculus, and the rate does not depend on the point in time. If this man is walking at 1 meter per second, then the shadow will be shrinking at 1/3 of a meter per second always, no matter where the man is. Now, that's the rate of change of S. I'm just going to throw this out and see to how many of you does it make sense. What is the rate of change of the tip of the shadow? D tip dt. How many of you know or see that it's -4/3 of a meter per second? Not too many. How many of you follow this logic? That the man is moving this way at 1 meter per second. He's dragging his whole shadow to the right at 1 meter per second. So if the shadow weren't shrinking, which would be weird, the tip of the shadow would already be moving that way at 1 meter per second. But it's also shrinking at 1/3 of a meter per second. It's like a boat that I'm in, and my line is in the water in this direction. I'm facing the back of the boat, and the boat is moving that way at 1 meter per second, and I've landed a fish. I've hooked a fish. If I don't reel in the fish will be moving that way at 1 meter per second, won't it? But if I'm reeling in the fish at 1/3 of a meter per second, that fish is moving that way at the meter per second plus the 1/3. So there's a way to reason it out. However, there is a really nice mathematical way to do it. You're going to call this distance t, better not use t, e for the end of the shadow. And if you want to know the rate at which something is moving, you have to measure it relative to a fixed point. So I'm using the lamppost. Do you agree that the location of E is equal to the sum of these two distances? Well, then differentiate that. The end of the shadow dt, do you see why I didn't want to use t? Equals ds dt plus dx dt. Well, we know these. This is -1/3. This is -1. So dE dt is -4/3. All I would say to you after this little exercise is be careful what you're asked for. 8 times out of 10, you're probably asked, find the rate at which the shadow is shrinking or growing. By the way, I have a correction to make here. So, picky correction, but I need to make it. But the odd time you're asked, find the rate at which the tip is moving. We have not directly answered the question. The question is, how fast is the shadow shrinking? The shadow is shrinking at 1/3 of a meter per second. Just to be picky, right? You're asked for the rate at which it's shrinking. So if it's changing at -1/3, then it's shrinking at 1/3. On the other hand, how fast is the tip of the shadow moving? The tip of the shadow is moving at 4/3 of a meter per second. How fast means how fast, no direction. So now that question, Damon, you were wondering about number 10, you can tackle that question. Speaking of questions, does anybody have any about this example? Okay, we're going to finish off with an example that is a little cumbersome, but it's not really complicated in terms of the level of thinking, I don't believe. We have a trough, something that you'd fill with water for cattle or whatever, that is 1.5 meters long, and it has a cross-sectional shape of an isosceles triangle where the two equal sides are a particular length and the angle between them is a particular value. So what we're talking about here is something that looks like this, right? It's got a cap on this end and a cap on this end, but that's an isosceles triangular cross shape here. This is 90 centimeters, you're told. This is 90 centimeters, and the angle's 100. Okay? The length of the trough is 1.5 meters. That's this length. So you don't have to draw this, but what we are talking about is something that looks like that. Now, I didn't draw it particularly well to scale, because if I do expand that angle in here to something that looks more like what it should be, and we're looking at it askew, so it wouldn't be perfect anyway. If I do that, then you lose the details on this side of the trough, and it just doesn't look right. Okay? But this is what we're talking about. This is 90 centimeters. This is 90 centimeters. And this total distance here is 1.5 meters. And there's a hole in it. Okay, so this is filled with water. And you pop this hole, there's a cork in it, whatever, you pull the cork out, and the water is draining. And the water is leaving this at, I'm sorry, Alex, can you help me? Did it say 500 milliliters per second? Okay. 500 milliliters per second. That's a volume, by the way. That's a rate of change of volume. And a little bit of kind of elementary measurement math here while you're drawing this. A milliliter is a cubic centimeter. So if you look at a dice for a board game, that's about a cubic centimeter. So if I had a little box that was empty, like the size of a dice, and I poured water into it, that would be 1 milliliter of water. I think it's a little bit more than a cubic centimeter for a dice, but you get the idea. So let's start at the beginning here, because there's an awful lot going on. Is there a rate of change whose value we know? Yes. Now, I've chosen to, I guess, commit myself to a rate of change of the volume in milliliters per second. Is it per second? Yeah. And milliliters is really cubic centimeters. So we don't have to write this, but I am going to, in brackets, just indicate that this is cubic centimeters per second. And that locks all of my other variables and measurements into centimeters. I cannot use meters anywhere here anymore. Now, could I have figured out how many cubic meters that is per second? Yes, but it would be such a tiny number, it wouldn't be a good idea. I mean, 500 cubic centimeters, that's 2 cups of water, by the way. 500 milliliters of water, 2 cups. A cubic meter is a meter by a meter by a meter. Imagine me giving you a box that's airtight or sealed well, that's a meter by a meter by a meter, and you're going to dump 2 cups in over and over and over again and to fill it up. That should demonstrate to you that this would be a very tiny number in cubic meters per second. Okay? I would rather work with bigger numbers than smaller numbers. What are we asked to find? Find the rate at which the surface level is changing. Okay, so now what we need to do is distinguish between the trough and the water in the trough. I'm going to look at the end of the trough. This is the end of the trough, maybe drawn more to scale. Like, I don't know. Oh yeah, I did check. This is pretty close to 100 degrees. Okay, and this blue triangle, God, I hate the color blue. This blue triangle, I'm going to tone this down a bit. this blue triangle is the water in the trough, right? So the dv dt is what's happening to the water, not what's happening to the trough. And if we want to determine the rate at which the water level is moving, then we need to measure the location of that water level compared to something that's fixed. And that would be the vertex of the trough here. Longer story short, the height of the triangular cross-section of water is something that if we knew the rate of change of, that would be the answer to the question. If I call this h, because it is a height of a triangle, ooh, see, that's why I don't like that. That's horrible. Isn't that a horrible mix of colors to look at? You like that? Okay. Too bad. If we set it up in this fashion, we imagine it being this kind of situation, then what we're trying to find is dh dt. Great. So all we need is a formula relating h and v. That's it. And it's not nearly as tough as it seems like it's going to be. It's just that there's a lot of twists and turns to this little tale. So first of all, this shape is what we would call a regular solid. Meaning if I stood it on its end and I cut horizontal slices off of it, all of the slices would contain the same shape. So these are examples of regular solids, that I have this cylinder, and if I sliced a piece off and looked at the cross-sectional shape, it would be a circle. It's the same circle all the way through. A loaf of bread is pretty close to a regular solid. Your slices are all kind of the same, but you get near the end and things kind of fall to pieces, right? This, which has, I think it's an octagonal shape, it's a regular solid. We've got a prism, we've got a regular hexagonal prism. The bottom line is they're not getting narrower or wider or changing shapes at the ends. And the volume of any shape like that, we should really invest in some larger visuals, the volume of any shape like this is always going to be the area of the end times the height. Basic geometry of three-dimensional solids. Well, there's no real height here, but the area of the end is an isosceles triangle, which is uniform throughout. We can then multiply that by the length. So the volume here will be the area of the end times the length of the trough. And the end of the trough is as a triangle, so it's 1/2 the base times the height times the length of the trough. We have a ways to go yet. One of the things we can do, though, is put in for L 150. Because the trough is 1.5 meters long, that's 150 centimeters. And the trough is not shrinking. I mean, I suppose you can imagine a scenario in which there's some kind of mechanical procedure going on and the trough is getting shorter. Maybe it's getting shorter to bring the water level up for the short little animals so they can still reach the water. I don't know. Doesn't matter. But the 150 is constant here. So now what we have is volume equals 75 BH. And we want to keep H. Why? Because we want dH dt. We want to keep V. Why? Because we know dV dt. So now what we need to do is find a relation connecting B and H so that we can replace B with an equivalent expression that contains H. And this has to do with this triangle. And it really, everybody, it has to do with common ratios of triangles again. Except this triangle, the black triangle, we only know this dimension. We don't know anything else. If we knew this, if you knew, and please don't write this down, that this distance here was 70 centimeters, then you could say, well, you could say, I suppose, well, no, I'm going to take that back. You would need to know this height here, the depth of the trough, in order to set up those ratios. But we don't need to do that. What we can do instead is recognize that this is 1/2 of the base of the water. And this angle is 50 degrees. So what's the relationship between the base and the height? Tangent of 50 degrees equals 1/2 the base over the height. Opposite over adjacent. Listen, tangent of 50 degrees is just a number. It's no different than 5. Well, it's different than 5. But it's just a number, right? Please don't calculate it. When we need to calculate it, we'll calculate what tan of 50 is. But if I want to get rid of b, then I have to rearrange this for b. Well, I'm going to multiply both sides by h to get h tan 50, and then I'm going to multiply both sides by 2. Right? If I first of all multiply by h, this is what I get. You could treat this as a complex fraction and deal with it all in one shot, but I'm not going to. And then I multiply by 2, so b is equal to 2h tan 50. And I think this is the first time in this class where we've got an application where we're using trig, but it's just a number. It's not a function of x or theta or anything. So what are we going to do? 2h tan 50 is b. We substitute it in for b. And we're so close to being done here. We might have some, run-around work to do to find a value of h that we might need, but we'll see. Simplifying this, I get 150 tan 50. Oh my goodness, I didn't check. It was 100 degrees between there, wasn't it? And you're aware that if it's an isosceles triangle, the height will bisect the angle into 50s. H squared. Again, I want to highlight everybody that this is just a constant. This is no different in principle than differentiating 4h squared or pi h squared. You're going to swing that 2 down. dv dt equals 300 tan 50 degrees h dh dt. Okay, so I need your guys' help here. To find dh dt, which is what we're after, we have to know dv dt. Am I correct in saying dv dt was negative 500? Okay. Negative 500 equals 300 tan 50. In order to find dh dt, we also need to know h. Were we fortunate enough for the question to say, find dh dt when the depth of water is so much? Does it actually tell us the depth of water at that point in time? I don't think so. It gives you a volume. So this is where all the legwork is now. We have to take this volume of 120,000 cubic centimeters. I'm of the opinion anybody who functions in the world should know there are 1,000 milliliters in a liter. But I'm also aware that not everybody might know that. So we have to take that volume and find the height from it. But just like a question we went over that somebody had asked about, Craig had asked about, don't reinvent the wheel. You already have a formula right here at the bottom of the screen that you can use volume to find height from. So that's what I'm going to do. I'm going to put 120,000 here equals 150 tan 50 times h squared. What does that tell me? Give me a second here. I have to take 120,000 divided by 150, which is 12,000 divided by 15. Couldn't be bothered. 800, thank you. 800 over tan 50. And we need to take the square root. This is h. Is everybody in agreement? It is 800? Okay. By the way, 800 is 20 root 2. Because 800 divides by 400, which is 20 squared. So if you really want to, impress your family and friends and pets, you could write that. Am I right? Root 800 is root 400, root 2. Root 400 is 20. So that goes here. Root 1050. There's nothing wrong with a little exact value work. When I rearrange this for dH/dt, what do I have? I have 500 divided by 300. I also have to divide by 20. So that's negative 5 over 3. That's negative 5 over 60. That's negative 1